Okay, hi everyone. My name is Lori Steffi. I'm a postdoc at NERSC. I have a really cool job, so I'm excited to tell you about it. But first, I'd just like to say thank you so much for having me. I appreciate the opportunity to come talk to you. Thank you all for coming. And I'd like to tell you that everything I will show today was a team effort. So it was done in collaboration with Roland Thomas from NERSC and Stephen Bailey from the DESI collaboration. Okay, so I'll give you the punchline right away. We were able to make their spectral extraction run 5 to 7 times faster, or actually give 5 to 7 times more throughput, which is even more meaningful. Maybe this makes you more willing to listen to me for the next 25 minutes. So how did we do this? I'll talk in a lot more detail, but we first profiled the code. We took real data to see where we should spend our time trying to speed it up, and we sort of had a two-pronged approach to how we ultimately did speed it up. The first one was making major restructures, and the second one was using Numba to JIT compile expensive functions. So these two things together bought us our speedup. And I will talk briefly about using Dask instead of MPI. Ultimately, we decided to stay with MPI, but I'll talk to you a little bit about why, because we really did like Dask. And our next task, now that we've sort of sped things up satisfactorily on CPUs, is to get their Python running on GPUs. And I don't know how many of you have tried that yet, but it's a little more challenging, as we are finding. Okay, so what is DESI? This is the science team that we are working with, and they are the Dark Energy Spectroscopic Instrument. They are going to be, or they are right now, installing their instrument as we speak in the Mayall telescope in Keep Peak, Arizona, which is outside of Tucson. And the reason why DESI exists is to help us better understand dark energy. So you may not know, and I didn't know either until I started working with this team, that we estimate right now that 70% of our universe is made of dark energy, our best understanding at the moment, and we don't really know what that is. So like good, curious human beings, we're trying hard to figure that out. So that's what DESI is trying to do. And what will they do? They are going to make the most detailed 3D map of the universe ever, which is, I think, extremely cool. It's going to take them 5 years, and they're going to systematically take images of the night sky, and they will send us their images every night for 5 years. They're going to make this map. They can use that to sort of test different theories of dark energy. I am not a cosmologist, so if you'd like to know more in more detail about what they're doing, please check out their website to answer any of your burning questions about them or dark energy. Okay, and what is NERSC? This is where I am. We are sort of the workhorse supercomputing facility for the Department of Energy. So if any of you have DOE grants, probably you'll be sent to us. And we have 7,000 users. We're located in Berkeley. And it's our job to help these 7,000 scientists get their science done. And so we support a very broad range of people, many of whom are Python users. In fact, 10 years ago, someone said, "Will you install Python?" And they said no. And now, I think over half of our users are Python users, which I think is great. So our current system is Cori, which you'll see here, and it's a CPU system. It's made of Intel Haswell and KNL CPUs. And our next system coming in late 2020 is called Perlmutter. All of our systems are named for scientists. And it will be made of AMD CPUs and NVIDIA GPUs. So I'll mention more at the end how we're getting ready to consider how to get DESI running on Perlmutter. All right, so you might wonder, I mean, the whole point of this talk is speeding up the DESI code, and you might wonder, like, well, why bother? As I said, DESI is going to take images and send them to us every night for 5 years, and 5 years is a lot of time, and that is really going to generate a lot of CPU hours. So every little bit we can shave off helps. So they'll take these images, which look like this banded thing you'll see, and they send them to us. We do all kinds of fitting and cleaning and extracting. We send them back their science. And this is real for them because based on the analyzed data, they decide, okay, this object we thought was a galaxy is actually a star, we can ignore it. Or we didn't get enough time on this exposure, we better do this again. So they'll use the data that we can provide them to plan their next night of observing. So the sooner they get that back, the better. And it's good for us, too, to speed their code up, because as I said, we support 7,000 people, and that means for every CPU hour DESI's using, that means somebody else is waiting in our queue. So it benefits everybody if we can speed them up. So that was our task. All right, so DESI's going to start commissioning this fall. And like I said, they want fast turnaround. And because DESI is somewhat developer limited, like any good science project, they never have as much money as they need, they really prioritize quick, clear, maintainable code. And for that reason, they chose Python. Usually I have to explain and defend this decision, but in this audience, you guys get it, which is fabulous. And they said, we know that we've asked you to speed your code up, but please don't rewrite it in C or Python. That's really difficult for us to maintain. So they said, please keep it in Python. That we have this one really expensive part of our pipeline called spectral extraction. So this was the piece we focused on, and it was our goal to speed this up. Okay, so in case you're wondering exactly what is happening in the code that we've been tasked with optimizing, DESI sends us images, which look like these, many hundreds of these or more a night, which are the data coming out of the fibers, which are pointed at objects. So this axis is fibers. This axis is wavelength. And so they sort of get this raw CCD image. We perform magic. And then they get out their clean spectra, which is what they want for their science. If any of you remember these kinds of plots from your physics or chemistry class, this is what they need. But how do we get to that? We're doing a lot of sort of expensive 2D fitting, which they call spectral perfectionism. We're doing some eigenvalue decomposition. We're evaluating special functions. And finally, we just have a lot of bookkeeping that's like, where are you in the image? Which pixel corresponds to which wavelength? So we have sort of a wide variety of things that they're doing. So it's not as simple as just speeding up, say, like one function. We have a lot of moving parts. Okay, so in my situation, someone hands you their code on GitHub and says, okay, postdoc, please make it faster. And so where do you begin? It's not obvious where the slow part is. And should you spend your time reading through all their lines of code? Emphatically, no. What we did is we used profiling tools to gather data on their application. So we weren't wasting our time. And chances are, whatever you think is slow is probably not actually slow. So it's much better to just take data. We're all scientists, so I guess we're on the same page. So we started with the easy tools, and then we progressed to the hard tools. And I don't know if any of you have much experience with Python profiling, but it's a lot easier than you think if you don't. The easiest easy tool, in my opinion, is cprofile, which is a built-in module for Python. And if you'd like to profile your code, this is what it looks like. You use M and invoke the cprofile module. You say this is the output file I'd like, and it's human readable. You point it at your script, you use your arguments, and then, yeah, now you have a lot of data that shows you exactly where time is spent. It writes a human readable file, but I think visualizing it is better. So this is my opinion. Your mileage may vary. There are two very nice tools for visualizing the cprofile output. And in fact, there are more, but these are the ones that we looked at. There is SnakeViz, which is very nice. It's browser-based. And you can interact with this plot in your browser. So you can click on it. You can expand. You can change this into an icicle plot if that's what you prefer. So this is nice. I didn't like this as much because loading something in your browser is kind of a pain. It's hard to email to somebody. What I did like was this tool called gprof2dot, which is someone's nice project on GitHub. So give them some props. And it just generates this really nice plot that shows you exactly what sort of the flow in your application looks like, and it's color-coded according to how much time is spent in each function. So it's really clear right away where your code is spending its time. So you can see here, this is Warren Hotspot. I'll talk a lot about this in the next 10 minutes, I guess. But this is one that we worried about because it was a major bottleneck. Okay, great. So you get this information from cprofiler, but it's sort of at the function level. Maybe it's not clear what in your function is really slow. So the next tool I recommend is also someone's project on GitHub. It's called Line Profiler. And this is a great tool. You decorate a function that you would like to know more about. And then it gives you this great sort of text file, human readable, and it shows you, I guess you guys can't see very well, but it says how many times it hit, how many times it spent on each line. So this is great because now you can say, okay, this NumPy function or this SciPy function is really slow. And for almost all the work that we did in this study, these two tools were enough. So you don't need anything really heavy to get started. I mean, you can move up to the heavier tools, but I recommend starting easy, and then as you need more information, using the bigger tools. Another one we have used, which I found not as intuitive, sorry if there's any Intel folks in the audience, is Vtune, but it's a little tricky to get out what you really need. You can see there's a lot of stuff going on. Sometimes it's hard to display the whole call stack. A tool that I liked better is called Tau from the University of Oregon. It's trickier to use, and you kind of need to build it for what you care about. So for us, we built it for an MPI application on a Cray system, which is what the NERSC systems are. But you can see when it works well, it could show us what all 32 of our ranks were doing, which if you are running an MPI code like we are, is really valuable. Also, there's another tool that I just tried called ARMForge profiling for Python, and that's good too, but I don't have a slide about that. Okay, so this is what worked for us. If you or any of your colleagues are embarking upon a mission to speed your code up, you might consider this workflow. Like I said, your mileage may vary. But start with the easy tools like cProfiler, visualize them, find your hotspot, get some more information if you need it, and then decide on your strategy. So, okay, you found a slow NumPy function, now what? Are you going to JIT compile it like we did? Are you going to adjust your code to call this function less? Or to call this function with smaller matrix sizes, for example? So that's the part where we can't tell you the answer. You have to find that out. After you fix something, check it and see that it actually did speed your code up. In some cases, we found things that we tried didn't help. So it's good to know that right away. And then rinse and repeat until you have as much speed up as you like. Okay, so I mentioned I was going to talk a lot about this particular hotspot, which is called legval. You'll find this if you look at NumPy's source code in their polynomial Legendre library. DESI loves this function. They were calling it all the time. It evaluates a Legendre series, which is good for their fitting. And so there were two problems with this. The first is that if you look at the source code, you'll see that the NumPy function is in Python. A lot of NumPy is in C, which makes it fast, but this particular function wasn't. So that was strike one. Strike two is that DESI was calling it a lot, and especially with scalar values. This function is totally capable of handling vectors, but they had written their code to call it with scalars. So it's expensive, and they're calling it too much. So we did two things to address this, and I'll sort of use this as a case study. We made a lot of other fixes in the code too, but these two sort of demonstrate our overall approach. Okay, I mentioned our first strategy was JIT compiling. So we used Numba. Anybody use Numba? A few hands? Okay. I like it a lot. I recommend checking it out. It's this nice JIT compiler. It's LLVM under the hood. So that means your Python interpreter is walking along. It comes to this function. You've got a decorator, and then it compiles it. And this makes it a lot faster than traditional Python code. There are a few gotchas. It has to be in a function that Numba will accept, or in a form Numba will expect. So you can't have type checking or some of the other things Python will let you get away with. You have to be a lot more explicit because it needs to know at compile time. Right now it doesn't support SciPy, so that's why I have a sad face. So if you have SciPy functions, Numba is maybe not a good candidate. Or in our case, we had to rewrite the SciPy in Python, and that was the workaround we found. But anyway, once you can get it in a nice form, your function will probably be faster. So just to give you an idea of what that looks like, so this is the legval function. This is pulled straight out of the NumPy source code. I've removed the doc string, otherwise it took up too much space. But this is the function. You can see we've got some is instance and other type checking, which we're not allowed to do, so we had to pull that out. And the onus is on us to make sure we're giving it the right thing. We knew our application really well, so we weren't going to need these cases in our loop. And our after function, we've added this decorator. So that's where you say, okay, please JIT compile this. we had to make this change here so that our arrays are not changing size, which is not allowed in Numba. And then after these sort of simple changes, which were kind of tricky, this bought us a ton of speedup. So on our KNL nodes, we got 16 times faster for this one function. And this is because we have these AVX 512 vector units, and it can do a good job of taking the vectorization, taking advantage of the vectorization, and 5xon has well. So with these sort of minor changes with Numba, you can get pretty substantial speedup. So I highly recommend checking it out. Okay, our other more painful strategy was restructuring the code. So in our case, ledgeval was being called down here at a lower level too many times. We wanted to call it earlier on in the code with a larger array, store the values, and look them up later. So that's what we did. This was kind of painful and took a while, but ultimately paid off more than our JIT compiling. So just to show you, after all of that work, we have this nice change at our lowest level. So we used to be calling this function eval, which was a wrapper for ledgeval, many, many times. These are scalar values. And instead, we had pre-computed and stored the value in ledgeval dict, and we were just looking them up. So this was way better. Okay, so I told you it was faster. Yes, it is faster. Okay, so NERSC had 3 systems when we started this study. Edison was our old system. This was our baseline, sort of our time to beat. This was our red dotted line. So my whole goal was to try to make our KNL nodes as fast or faster than Edison. So you can see once we got to here, we beat Edison, so that was good. But I mentioned before, sheer speed is not as meaningful to DESI as how fast can we process our images. So this plot I like to show more, even though it's not as impressive, because this is more indicative of their actual science. So this is, again, the list of all of the things that we have done in this study in chronological order. So this is before we touched the code, and this is sort of now. And yeah, so for DESI, this 5 to 7 times more throughput means that at the end of the year, they will reprocess, at the end of every year, I guess, for 5 years, they'll reprocess all their data with their latest pipeline. And before that meant it would have been 33 million CPU hours to get that work done, and now it's more like 7. So that's real savings. That's awesome. DESI's happy with that. We're happy with that. So we're really glad we were able to do this. Sort of the lesson that we have learned through this is maybe not the answer that you want, but the restructures, which were more work, ultimately paid off more also. So here's that same plot I just showed you on the left, and then on the right, we're plotting the incremental speedup. So how much better is each change as compared to the previous one. And the red arrows are showing you the restructures. So yeah, they definitely benefited more than our little JIT compiles. So our lesson to you, audience, is that don't despair, because in our experience, the time you spend is proportional to the speedup you get. So it's not a step function. Of course, there's some learning curve because you'll need to learn the tools. But once you do, even if you have a little bit of time to spend, you can get a little speedup. If you have a postdoc like me and you want to spend 1.5 years, then you can get a lot of speedup. So yeah, I would recommend, even if you don't have too much time to devote, you can still benefit. Okay, I mentioned, to change gears, that we considered Dask, replacing the MPI in DESI's code with Dask. If you're not familiar with Dask, I would recommend checking it out. It's a nice way to handle distributed workloads in Python. You have these really nice Bokeh visualizations, so you can see exactly what all your workers are doing at any given time. It's nicer and more flexible and more modern than MPI. So yeah, we wondered, can we rip out the MPI and put in Dask instead? After several months of really looking into it, we decided no. And not that there was anything wrong with Dask, but just that we already had an established code, and it's really difficult once you have built a project to change the method of parallelism. So if you're starting from scratch, I recommend checking out Dask. I'm happy to talk more about this, by the way. All right, and finally, I said we're getting a new system in 2020, and it's going to have a lot of GPUs. And so change is the only constant in life. We've worked really hard to optimize DESI's code for our CPU system. Now we need to sort of do it again for our new system. It's good for me, because it keeps my job interesting. Yeah, so getting Python running on GPUs is somewhat tricky. Has anyone here been experimenting with that? Yeah, okay, so I'm relatively new to this as well, so maybe you guys know more than I do. But our questions are, how can we get DESI best using our GPUs? And should we use the same optimization approach that we used for CPUs? And my feeling is no, having looked at my colleagues and similar work that's been done. Rather than just optimizing these expensive functions like we saw earlier, I think we're most likely going to need to rethink how we're dividing our workload. Right now, DESI splits its images into small pieces. And for a GPU, that's the opposite of what you need to do. So I think we're looking at more of a major restructure than these sort of minor improvements that we made. Another question we have is, what is the best way to do this in Python? So far, we've tried CuPy and, of course, our friend Numba. Although Numba for GPUs looks a lot more like CUDA than it does Python. So that's, yeah, and it's not portable either. I mean, ultimately, we'd like something that can run on any system and any hardware. Anyway, so this is still work in progress. We're trying to decide what the best way to get them running on our GPUs is. All right, so in summary, we were able to help DESI speed their code up or increase their throughput 5 to 7 times without rewriting in C. So it stayed in Python. We honored their original request for us. Their yearly reprocessing dropped about 25 million CPU hours, which is substantial. So that's great for them. They get their science results faster. And that's good for NERSC, because now we have resources to give to somebody else. We accomplished this using 2 main types of improvements. The first was JIT compiling with Numba, and the second was taking a long, hard look at how your code is structured and making changes to avoid expensive functions or make them a little less bad. So coming up now, our future work is figuring out how to get DESI running efficiently on our GPU system. And if you'd like to know more, we have a whole website where we sort of lay out the profiling strategy that I discussed quickly earlier. So if you have any questions about how to profile your Python code, hopefully this is a good resource. I wrote it, so if it's not helpful, please tell me, and I'll make it better. If you want to see what DESI is doing and which parts of the code that we've touched, you can find them on GitHub. So if you're just curious what it looks like. And finally, we have a paper in the SciPy proceedings, so you can find what I just talked about here in a lot more detail. So thank you very much.
So do we have any questions?
Hey, awesome talk, by the way. The speedups you got are definitely not an easy thing to do, so kudos for that. The question I have is, looking at the 2 optimizations you made, have you tried combining the 2 and maybe JIT compiling the restructured code?
Yeah, I guess, so for Legibel, what you see here is oh, thank you, is kind of a combination of both. So this is the JITting the actual function without the restructure. And this is, once we did add the restructure with yeah, so this is sort of 2 combined. Yeah, so for that function, we took a 2-pronged approach because it was such a bottleneck for us.
So the 16x speedup was from using both?
Actually, no, the 16x was just Numba. So I didn't, I could go back and measure the 2 together, but I actually didn't do that. Yeah, so in that case, yeah, just the Numba itself was a big help.
Other questions?
Yeah, so I just wanted to say that was a really great talk. I have one question though. How do you ensure that the behavior that you see when you're profiling is the exact same behavior when you're executing, and ensuring that the code's performance on like the test data set is the same on when they're actually running it and doing the analysis and the translations?
Excellent question. Okay, so, oh, sorry. I had a few times when I was new and I was testing not under the conditions that we expected to run. So like I profiled something on my laptop and I was like, ooh, a lot of speed up. And then I moved it to our real system and there was no speed up at all. So I would say number one, always optimize on the system that you plan to be running on. Yeah, right now we don't have any real data, so we have simulated data. And we do, I guess the assumption is that it will be representative. Maybe it won't, but I guess we'll adjust and see. I think this is one of many such surveys, so I hope there are no surprises for them. They sort of know what to expect. But yeah, I would say definitely profile under the best, most realistic circumstances.
Yeah, this is great stuff. Really useful to see both how to do this and the incredible speedups you managed to get. But I'm curious if you've thought any about how to sort of make this available to the wider astronomical community, whether this code could be sort of passed up to some of the larger open source projects or just made into a sort of open source project on its own, not DESI focused.
Very good question. So I'm sort of new to this world and this field. I've really only been doing it for about 2 years. So if you have suggestions, or if anyone has suggestions about how to make this more available, I'm happy to take them. I mean, the DESI code is publicly available, and I think it's up there. But yeah, I guess people wouldn't know that it's there, where to look. So we're happy to share it. Just if anyone has suggestions, let me know.
Any other questions?
Hey, thanks a lot for the talk. This was just a comment rather than a question, but I just thought I'd share that I've had similar experiences in other domains, profiling, and I have had cases where the addition of line profiling dramatically and fundamentally transformed the performance behavior of the function that you were profiling.
You mean by adding overhead?
Yeah, particularly the overhead of line profiling can totally transform the behavior of a function. So I just wanted to say that in case anyone else.
Yeah, I guess I
the
should
same
have
thing.
stressed a word of caution. Most profilers will add some overhead, and then it's this sort of Heisenberg problem of trying to measure the thing that you care about. But we didn't run into that problem, but I could see that if you had a small or a code that ran short, I guess you can sort of insure against that by having a longer simulation. But yeah, I guess be mindful, your profiler will add some overhead. Yeah.
A comment maybe. So the line profiler is written by Robert Kern here from NSOT. So we have him to thank for that.
Thank you.
The other question I had there was about the splitting of images up that last restructuring step that were proposed. The way I understood it, it was necessitated by complexities of linear algebra on an image.
Yes.
So if you do it on any sort of hardware, your mileage vary. You may need to chunk it up in a larger pieces, but I think you can't avoid, by math of it, you can't avoid processing a single image on a GPU or a CPU. Memory is not a concern. It's a sheer computational complexity.
Yes, that's an excellent point. So we have split this into pieces that we know work really well for our CPUs. And I think you were part of the team that recommended that fix, right? No? Okay. All right. Well, so we cut it into small pieces that we know work well, because the linear algebra does get really expensive as you increase in matrix size. And for GPUs, we can maybe get away with different dimensions than for CPUs. But yeah, we probably can't escape having to cut it in some number of pieces. But that will be part of my job is figuring out where that sweet spot is.
Maybe one more quick question, if we have one.
Thanks for the talk. Could you just briefly elaborate on kind of what metrics that you evaluated when you were looking at Dask and how that compared to MPI?
Well, I guess our like zeroth order question was, is it possible to replace our MPI with Dask? A lot of things we liked about Dask, like if you have a huge MPI job and one of your nodes goes down, your job is done. With Dask, we really liked that the workers could come back and continue. We also really liked this Bokeh visualization where you could see what your job was doing in real time that MPI can't really provide. So there was nothing wrong with Dask. It was just that DESI was, it was too much for us to transition this already MPI code over to Dask. We can talk more, I guess, if you have specific questions. So yeah, we really liked it. It just wasn't feasible for us.
Thank you. Let's thank our speaker.